We are now going to talk about clipping and rasterization. We'll do this over 2 lectures. So specifically, the topics that we'll cover are line clipping. How do you clip lines to get line segments? We will see how this extends to polygon or triangle clipping. A related topic to clipping is visibility and hidden surface removal. So we'll talk about that. And then in rasterization, we will start by discussing how to rasterize line segments using a very popular algorithm. And then talk about a generic approach for filling in polygons or triangles. The reading for this is again from Angel. So as I mentioned, so we are now talking about clipping and rasterization. So these are the later stages of the graphics pipeline. So we are done with processing the geometry. So the vertices are processed. We can assume that they are assembled into primitives. We did not talk about this stage explicitly, but it's a fairly simple stage for now. So essentially vertices get collected into the primitives that are already declared. So after this, we want to clip the primitives that lie outside the view volume. So this is done in the clipping stage. The rasterization stage is where we try to identify pixels that are affected by the primitives that lie within the view volume. So essentially convert the geometry into a raster image. Some of the tasks that belong to clipping or rasterization are postponed and taken up in a later stage called the fragment processing stage. So for example, a task called hidden surface removal is done at the fragment processing stage. So is anti-aliasing. Let us talk about clipping. So what is clipping? If you have done a course on graphics in your undergraduate, then you have probably looked at clipping 2D objects against a clipping window. What we will talk about in general is clipping 3D objects against clipping volumes, although I will begin with examples in 2D so that you get the intuition for the algorithms. The techniques here are classic. They were developed in the 80s. The techniques are actually easy for line segments and for polygons. They of course become difficult when you want to handle curves and text. One easy way to handle curves and text is to convert them into lines and polygons and apply the previously developed algorithms. So here is a pictorial representation of what clipping essentially produces. So what you have in the black rectangle is the clipping window. Let's begin by talking about clipping 2D line segments. So we want to clip the blue line segments here and identify the ones that lie inside the black clipping window. The brute force approach could very well work. So what is the brute force approach? You compute the intersections of the line segments with all 4 sides of the clipping window and use that point of intersection to decide which line segments lie inside and which lie outside. And for line segments such as EF, you also determine the portion of the line segment that lies inside. So this is clearly inefficient because every intersection calculation requires 1 division because essentially every intersection calculation is reduces to the solution of a simultaneous system of equations. So Cohen and Sutherland developed what is now a classic algorithm, where the idea is to eliminate as many cases as possible so that you minimize the number of intersection calculations. This is key. So how do they do this? So first of all, note that we would like to do clipping against this simple clipping window. Let's start with this case. The four lines x equal to x min x max, y equal to y min y max, these four lines determine the clipping window. Cohen and Sutherland identified different cases and gave a recipe for handling each case. Case 1 is where both endpoints of the line segment lies inside all the four lines. So in this case, we naturally would like to draw the entire line segment. Case 2 is where both endpoints lie outside and on the same side of one of these lines. So for example, here the line segment lies outside x equals x max. So this is again a special case, right? So you have the two endpoints and both of them lie outside x equals x max. So by outside I mean in the direction that lies outside of the clipping window. So in this case, naturally, we would like to discard the line segment. The third case is where one of the endpoints lies inside and the other lies outside one of the bounding lines, right? So in this case, we cannot avoid an intersection test. So that's what we do. The fourth case is where both endpoints lie outside. But you may have multiple cases. Here is another case where both endpoints lie outside. In the first case, you would like to reject the line segment and clip it out, whereas in the second case, you do want to intersect it with the clipping window and find this line segment that lies inside. So again here, we need to perform at least one intersection test. Cohen and Sutherland implemented this in the following way. So for each endpoint of your line segment, they defined an outcode. So let's call this outcode as B sub 0, B sub 1, B sub 2, B sub 3. The outcode takes values 0 or 1 using this recipe. So the recipe is not too difficult to follow. So the values are, like I said, at 0 or 1. The value of each bit here tells you if you are on the appropriate side of the corresponding line. So for example, B0 corresponds to Y max. So B0 equals 0 means that you are below the Y equal to Y max line, and so on, right? So points inside the clipping window will have all zeros as the outcode. So the outcodes clearly divide the space into 9 regions. Computing the outcode takes at most 4 subtractions. This is clear. how do we use the outcodes? So consider the 5 cases that we saw earlier. The first case is AB, where both endpoints lie inside the clipping window. In this case, your outcodes are both 0, and you can find this with a simple AND operation. With a simple OR operation, and you accept the line segment. The second case is, let's say, something like CD, where one of them is 0 and the other is not 0. So the way you proceed with this is you want to find the intersection point. So this will proceed as follows. So who do you intersect with? So you decide which line to intersect with by looking at the 1 in the outcode of D, and you use that to decide which line to intersect with. So in this case of CD, we will intersect with x equals x max. Of course, D could have 2 1s. So for example, D, instead of lying here, it could lie here. And in this case, it will be to the right side of x equal to x max, and it will be above y equal to y max. And so there will be 2 1s in its outcode. And in that case, we may have to do 2 intersections. Another case is something like EF. So here we use a simple AND to decide, bitwise AND, to decide if we would like to reject this line segment. Because it naturally lies outside the clipping window. So we reject. So the remaining 2 cases are the more involved ones, GH, IJ. So of course GH and IJ do not fit in under any of the earlier cases. So they would not pass through the earlier cases. So what do you want to do here? How do you process GH, IJ? You would like to shorten this line segment. And the way you do that is by identifying one of the lines with which you want to intersect. So for example, for H, you can decide based on its outcode that you want to intersect with the y equals y max line. And now we can compute the outcode of this intersection point. So now you have G and the intersection point. And we can use this shortened line segment and re-execute the algorithm. So this is how the Cohen-Sutherland algorithm proceeds. So how efficient is this algorithm? In several applications, what happens is that your clipping window is much smaller relative to the size of your data. Often you are looking only at a small part of the data. Or in the other case, you are looking at the entire data. So in both cases, what happens is several of the line segments are either to be accepted or to be outright rejected. So the Cohen-Sutherland algorithm will eliminate the majority of these cases via the outcodes, and it will reserve the intersection calculations to only a few cases where you have line segments crossing the clipping window. The only stage which is inefficient is when your code is re-executed for the last case, where the line segment needs to be shortened. Thankfully, this happens to be infrequent, and so Cohen-Sutherland works quite well in practice. So Cohen-Sutherland in 3D works the same way. You have 6-bit outcodes, and the clipping now is with respect to planes rather than lines. And you have 27 different regions. Each one gets a 6-bit outcode. So just to recap what we talked about in the previous lecture, I think last week, on normalization, view normalization. General clipping actually requires you to compute intersection points between your line and an arbitrary plane, because typically your view volume or a view frustum is bounded by planes. So for example, in an oblique view, you do have something like a parallel pipe. So to avoid this difficult computation, we said that we perform view normalization, where the view normalization will convert the view volume into a cuboid. Of course, in this process, it may distort the object, but if you follow view normalization with orthographic projection, then all is good. So note that normalization is a viewing transformation. And post-normalization, we are able to clip against a very simple right parallelepiped, so which is essentially a cuboid. So the kind of intersection calculations that we want to do now will essentially be just a simple floating point subtraction. This is easy to do. So this is one of the benefits of view normalization, and essentially with respect to how it affects the clipping process. Now that we talked about line clipping, let's move on to polygon or triangle clipping. It's clearly not as easy as line segment clipping, right? Because, for example, like what you see here, the polygon could intersect the clipping window multiple times, and the resulting polygon could have multiple components, such as this. Of course, if your input polygon is convex, then after clipping, you continue to get a single convex polygon within your clipping window. So one solution to handle generic polygons is to replace your input non-convex polygons with a collection of triangles. This is what we have done. This is called tessellation. So a tessellation converts a polygon into a bunch of triangles. This simplifies our clipping, as we will see. More importantly, it simplifies the later stages of the pipeline, for example, rasterization. So in order to perform polygon clipping, let's think about clipping as a black box. So this is a different approach to clipping, different from what Cohen-Sutherland attempted to do. So the idea is this: you want to think about your line segment clipping as a process that takes two vertices in. So the two vertices are shown here, x1, y1, x2, y2, and produces either the same vertices as output, so which essentially means no clipping, or it produces a clipped line segment. So for example, here the clipping is with respect to y equals y max, and so in goes x1 y1 x2 y2, and the out line segment is the clipped version x1 y1 x1 y max. Right. So you may ask, how does this help us? We are actually computing intersections now, and multiple intersections. So the key idea is to put these different boxes into a pipeline. And we know all about pipelines and their benefits. So we can actually have 4 independent clippers in our pipeline, each one clipping against one of the 4 lines that form our clipping window. So now in goes your 2 line segments, 2 endpoints, x1, y1, x2, y2. And after clipping against all 4 lines, you will get your clipped line segment here. If the line segment lies outside the clipping window, then you get a null. Alternately, you could check for that case explicitly using outcodes and accept the line segment as it is for special cases. But let's talk about the simple case where every line segment goes through this pipeline with 4 boxes. So this idea works exactly as is for line segments and for polygons. So how does it work for polygons? You have a clip with respect to each of the 4 bounding lines. So in goes your, for example, triangle. After clipping with respect to the top line, you get a polygon, a clipped polygon like this, which is next clipped with respect to the bottom line, and the output is the same as here. Let's call it A. Next, after clipping with respect to the right line, so you get a smaller polygon which goes as is, and that's your output as shown here. So even though you employ 4 different intersection calculations, 4 different clipping boxes, since you pipeline them, you can think about 4 different triangles getting fed into the pipeline one after the other, and all getting processed simultaneously. So this is the benefit of this pipelined approach of clipping polygons. If you'd like to do this in 3D, of course, you can add 2 more clippers for the front and back plane. In fact, this was the strategy used in the first graphics hardware from SGI. And this was one of the early uses of parallelism in the graphics pipeline. So you can already see that this strategy will increase your latency. So the time to process each triangle may be slightly increased because it has to go through 4 stages now. However, you can process 4 different triangles at the same time. So the throughput actually is quite good. So this idea of using parallelism with possibly a small cost to latency is often used in graphics. So what we saw so far was clipping with respect to implementation in the hardware. Now, of course, you can avoid sending all those triangles to the graphics hardware and save the overhead of transfer. So how do you do that? If you employ efficient data structures to store your input, then you can already decide which triangles lie inside the clipping window or clipping volume and which lie outside. So one of the early ideas here was the use of bounding boxes. So the motivation is when you want to handle complex scenes, or which consists of complex polygons, then clipping is actually a costly operation. If you can avoid it, then all the more good for you. So the way you avoid clipping computation is by storing your complex polygon as a collection of axis aligned bounding boxes. Of course, you store the polygon also, but in addition to storing the polygon, you store its axis aligned bounding box as shown here in dashed line. So the bounding box is essentially the smallest rectangle which is aligned with the axis and encloses the polygon. This is very simple to compute. It's just a simple min-max operation on the x and y coordinates. So now what you do is to compute your clipping for the bounding box initially. So if the bounding box is accepted and goes through the clipping stage, then you are done. You send the entire polygon through the clipping stage. If the bounding box is rejected, then naturally your polygon is also rejected. So it's only in those rare cases where the bounding box intersects the clipping window where you need more detailed clipping. So the idea is again similar to what Cohen-Sutherland proposed. So bounding boxes are studied extensively. There are many variants: hierarchical bounding boxes, non-axis aligned bounding boxes, bounding spheres, and so on. So this is a big literature in itself and was also actively studied within the robotics domain. So next I want to quickly talk about another topic that's very much related to clipping, but is not necessarily done in the graphics hardware. So this is visibility. Clipping has much in common with, in general, hidden surface removal. So removing parts of the scene that are not visible to the viewer or visible to the camera. So things may not be visible due to many reasons. What we saw is procedures or methods for removing those objects that are not visible because they are outside the view volume. But there may be other objects that are occluded and hence not visible. So this is in general called hidden surface removal. In both clipping and in hidden surface removal, we want to remove objects that are not visible to the camera. And in both cases, the key idea is to reduce work. So we test for visibility, we test for occlusion as early as possible. And by doing so, we eliminate many triangles, many primitives from entering the graphics pipeline. If a particular triangle is not going to contribute to your scene, then you would like to remove it from the graphics pipeline as early as possible. So why process it if it does not contribute to the scene? So now let's talk about some data structures that aid in visibility testing. So we are now going to talk about visibility with a focus on data structures for answering visibility queries. So essentially we want to test for visibility. The motivation is more or less direct from computer games. Many of you may have played first-person shooter games. So you see only a small part of your scene. Everything else is not visible to you, either because you are in one room of the scene and the other rooms are hidden by the wall. Right? So in these games, interactivity is key. So you would like to remove as many objects as possible from entering the graphics pipeline. So naturally this will lead to efficient processing. It reduces burden on the pipeline, and more importantly, these are triangles that do not go on the bus between the CPU and the GPU. So how do you identify which objects are visible and which are not? So one of the early approaches was efficient storage of objects, so that you can quickly decide which objects are visible from the viewer and which objects are hidden. Right? So there are two popular data structures here. These are based on the idea of partitioning space. One is called BSP, the binary space partition tree, BSP tree. The other is called an Octree. Let's try to understand these data structures using examples. I'm not going to formally discuss the complexities here, but the complexities are not too difficult to derive. Let's take a simple example. So the idea is to understand or the intuition behind these data structures. And once you understand that, it's actually quite easy to implement. So here is a simple example. Let's consider 6 polygons or triangles. Let's assume that they are parallel to each other, right? And let's assume that you are looking at them in the normal direction. So the top view is going to look like this. So each of the polygons are parallel to each other. So the top view is a line essentially, right? So if it is not clear, the top view is from here for all of these polygons. So each polygon is you see it as a line segment. So from the top view, you can kind of see that the plane of one of them, let's say A, separates B and C from the rest. So this is the idea of the BSP tree. So what the BSP tree does is to bisect your domain using these planes. So for example, the plane of A separates BC from the rest. The plane of C now separates recursively the polygon B and the polygon A. On the other side, the plane of D separates E and F, right? So essentially recursive bisection. So you start with A, so that's 1, and then next you do you bisect using C on the left, and on the right you bisect using D. So this bisection can be stored in the form of a tree, and this is the tree that you want to query for identifying visibility. So this tree was introduced around the time when this game called Doom was introduced. And this was one of the success stories of the BSP tree. The fact that it was used in Doom and immediately deployed. So what you see here is the tree, the BSP tree corresponding to the example that we saw. So querying the tree essentially means following a path in the tree. So if you give me any plane, so any plane here, let me try to draw that again. So if you give me any plane here, I can use the tree to decide which polygons are visible when I'm on this plane and let's say looking to the right. And the way I would do that is I would go to the root of the tree and decide if my plane, so let me call this plane X, if my plane lies to the right of A or to the left of A. If I lie to the right of A, I traverse the right subtree and so on. So I do this until I find the position of X. Once I find that, I can just simply report all subtrees, all nodes in the subtree. So in this case, I would report everything here as visible from X. A related idea is called the Octree. So in order to introduce Octree, let me first do something in 2D. So this is a Quadtree. So in a binary space partition, we used the data explicitly to partition your space. So we used the plane formed by one of the polygons to partition the space into two half spaces and so on. In the Quadtree, the idea is to make the partition simpler. So let's take the example of an image. There are filled pixels here and some of the pixels are unfilled. You partition this 2D space using axis parallel lines. And in one go, you partition the plane into 4 quads. And repeat recursively for each quad. So the idea is to get a tree like this. You can clearly see that the fan out here is 4, right? Corresponds to that's hence the term Quadtree. So this is the root node, and as you can see, one of the leaves is a filled node, so that corresponds to this guy, and one of the children is empty, and that corresponds to this, and the other 2 children are subtrees themselves. So which means that in those cases you need to further subdivide before you get elements that are either all filled or all empty. So with such a recursive bisection, you can store, for example, this image efficiently. So the image is really stored in these black leaf nodes. The idea of the Octree is similar, except that now you work in 3D and you do recursive bisection, and in one iteration you partition your domain into octants, right? And hence the fan out is 8. So your planes are axis aligned, and the fan out here is 8. So the Octree is a highly popular data structure. It's used heavily in graphics, but it's used equally well in robotics for collision detection and so on. And in graphics, it is also used for ray tracing. The Octree is actually a very simple data structure to implement. The fan out is 8, it's fixed, and it's essentially just like your search tree. Very easy to store your data in the form of an Octree. Now, depending on what task you want on the Octree, you will have to traverse different paths in the Octree. So this can get tricky depending on the task, but for simple tasks such as who lies in front of me and so on, traversing the Octree is not too difficult. So I will stop there for the discussion on clipping and visibility. Just to recap, we talked about clipping as as it is implemented in the graphics pipeline. So this is part of the graphics pipeline that is fixed. So we don't have any access to a shader here. And then we talked about visibility, particularly hidden surface removal in your application program. So we talked only about algorithms that are implemented in the application program for removing triangles that are hidden from the viewer. In the next part of this lecture, we will talk about rasterization. So converting the triangles into pixels or fragments.